presentation, online PID tuning of a 3-DoF robotic arm using Metaheuristic Optimisation algorithm, a comparative analysis.
Thank you very
Please
much. I'll select the
Yes,
slides.
okay, it's a moment. It should be okay.
Yeah, nice. Yeah, so this is a collaboration between the Kaunas University of Technology and the University of Agder. I am Filippo Sanfilippo. I am responsible for the group of biomechatronic and collaborative robotics research group. And this is just a brief overview of our research focus. I'll try to be short. So basically we work with different kinds of robots, and in this figure here we have categorized them into three main layers. The core layer is what we call carriers. So these are robots with different topologies, robots with legs, robots without legs, robots with tracks, robots that are flying, or robots that go on water environments. And these for us are just carriers. We can equip them with sensors and we can use them for different applications. On top we have what we call normally add-on layers. So this is what we can equip the robots with. So for example, we can have grippers, we can have arms or other sensors. But what we really care the most in my research is this layer here. Because we are not building robots just for the sake of building robots, but we want robots to collaborate with humans. So the human-machine interface is what we care the most. So, and here we can see some examples of how humans and robots can interact with each other. So for example, we have brain-machine interfaces that are becoming more popular, some hand gesture interfaces. And these first examples, this one and this one, are used for humans to send commands to the machines. But what if we can close the loop? What if we can get feedback from the machines back to the humans? Here we have an example where we do this. We have designed some devices that can give force feedback to humans. So if I am grasping this object with the robotic arm, I can transfer this force to the human that is still operating that robot. So just to give you an overview. And this is some of our PhD students working on these topics. So today we are going to have this short agenda. First I will introduce the idea behind this research paper, then the methodology will be discussed, then some results and some conclusions will be given. So I know that not each of us is coming from different fields, so I'll try to use simple words and try to be more interactive. So here we are trying to use a metaheuristic, like the ones that Marcin was talking about during the opening. So metaheuristics are shortcuts. So to solve a problem that is normally complex, and we try to get inspiration from nature. For example, the polar bear algorithm. Here we are talking about an algorithm that is inspired by war strategies. We are in times where war is maybe not the best topic to talk about, but we are scientists. We take inspiration from everyday or existing natural systems or other systems. So we want to use this metaheuristic or shortcut to solve a common problem in robotics, which is the control of a robotic arm. So basically, when we want to use a robotic arm to make a manipulation task, like lifting this object, I need to set the joints of my arm, right? to specific angles so that I can reach the target. So this will work if our world will be ideal, but unfortunately our world is not ideal. So we have different problems like energy dissipation, friction, imperfection in the mechanical design. So this means that even if I set my joints to a specific position, most probably I will not reach the target. There will be an error, right? So normally, traditionally, in robotics, we use, since many years, 20 plus years, since the beginning of robotics, we use PID controllers. So proportional derivative integral controllers that are really the basic controllers for robotics. So using PID controllers, we can actually minimize the error iteration after iteration so that with the robot I can really reach the target, or at least I can minimize my position error. The only challenge is that tuning a PID controller in real life is not simple. So this can be done traditionally with different methods like trial and errors or some more advanced methods, but the challenge becomes bigger when we have robots with, like this one, or even more complex robots with more than 3 degrees of freedom. So then we have a bigger problem. That's where we think that our proposed method can help. And our proposed method, so it's meant to tune a proportional integral derivative controller using a meta-heuristic, which is called war strategy optimization. So we propose basically a hybrid control algorithm that combines the war strategy optimization algorithm with the PID controller to tune the key parameters of the controller. And here just a small reminder to ourselves, like we can have several meta-heuristic algorithms. Some of them are single agent, like I believe the polar bear algorithm. The one we are presenting today is a multi-agent algorithm. So it's basically, as you can see here, the idea is we have several agents that are exploring the search space in a multi-dimensional space, and iteration after iteration we try to reach our target. So, and there are several ways to do this. Today we look at one algorithm that is inspired to war strategies. Some of the challenges when we use such algorithms that are heuristics or meta-heuristics is that in an ideal case we might have only a single minimum or maximum in our search space. But in real cases, we unfortunately find ourselves in this situation where we have multiple maxima in our search space. So the risk is that we get stuck in a point that is not optimal. So with this meta-heuristic, we try to be creative and try to avoid to get stuck in a maximum or minimum that is not what we want. We try to find the optimal one. So how does our proposed algorithm works? As in war, we have an army, and the army is under the command of a commander, and then there is a king. So at each iteration, the commander is leading the army, and the king instead as a legacy is the one that, so let's say that each iteration is a battle, right? The war is longer than a single battle. So the commander can change battle after battle, but the king is normally staying for a longer time. So these two key elements are the ones that are leading the army and the other agents. And at each iteration, we are assessing the fitness of all the soldiers. So each soldier has the same chance to become a commander based on how strong, how fit is the soldier itself. And basically by leading the army towards our search space, we try to find the local minimum or maximum, the optimal maximum or minimum, the global one. So here we have a flowchart with how the Metaheuristic is integrated with the tuning of the PID. So basically the first step, we calculate the cost function value using our model, which is implemented in Simulink. And then we run the war strategy optimization algorithm, and we get the values of our parameters for the PID, which are 3 parameters. The K parameter, which is the proportional gain, the P parameter, the D parameter, which is the derivative term, and the integral term, which is I here, or yes. So Kp, Ki, and Kd. So then we use these parameters and we run one control iteration with our robotic arm. So that means that basically we move the robot to the target position and we assess the error. So are we getting to the target position or we are still far? If we are still here, it means that there is an error in the Cartesian space, x, y, z, and the roll pitch IO for the end effector. So basically, we run this control and we measure we take the feedback, we measure the error, and we send it back here. So here we are assessing the error, which is the difference between the target position or desired position and the actual position. So that error is then fed again into the loop for the next iteration. And we have considered 2 existing or alternative metaheuristics to compare our proposed method with. And here in particular we are considering particle swarm optimization and gray wolf optimization, which are well known in the field. And these are the values that we have used for implementing these competitive algorithms. Here you can see the simulation environment. These are taken from Simulink. We have our, basically it's a block-based programming environment. We have our signal generator, which is the one that is generating the signal, like for example, for the end effector to follow. Then we have the model of our manipulator with the implemented PID controller. And then here we have a set of cost functions that we consider, particularly the error in the Cartesian space. And here we have some way to measure our errors. So here is just a short video. Can you please click on it? So this is the environment. So as you can see, iteration after iteration, we try to reach a desired position, which is more or less here. We go there and we assess the error. If the error is normally, at least at the beginning, very big, so iteration after iteration, we try to minimize that error. And we tune the PID with the parameters that are spit out from the war strategy optimization algorithm. And then iteration after iteration, we can minimize the error. So here we can see the results. Basically, this is a comparison with our algorithm, WSO, against the particle swarm optimization and the gray wolf optimization. For the 3 joints, we have a robotic arm with 3 degrees of freedom. And so this is in the joint space, a comparison in the joint space. And as you can see, WSO is performing very well compared to PSO and WSO in this specific case, because the error is much lower. These are the gains that are extracted from the 3 different techniques that we are analyzing. So for each joint we have the proportional, integral and derivative term, and here is the same results but shown from in a diagram perspective, iteration after iteration. So the black line is the proposed method, WSO, red is gray wolf, and blue is particle swarm optimization for the 3 joints. So as you can see, after some time, after a number of iterations, the black line goes below the 2 competing algorithms. So that means that we are getting better performances over a number of epochs. And here is some more results related to how good is the response of the controller to a step input. So that means how fast the algorithm is converging to the desired position. So again, here we have blue is red is the proposed algorithm, green is gray wolf, and purple is particle swarm optimization. The dashed line is the set point, so it's our step input. So that means that all the 3 competing algorithms are converging, but the red line is faster and relatively more smooth. So there are no spikes. So that means that our end effector is not vibrating or oscillating while reaching the target position. So to conclude, in this article we have presented the meta-heuristic based algorithm that we call war strategy optimization, and we have used this heuristic to tune the controller, the PID controller for a robotic arm. And we have compared it against 2 standard methods, particle swarm optimization and gray wolf optimization. And the simulation results show that the proposed method performs better in terms of error in the Cartesian space and the joint space, and also in terms of response to the step input. So, of course, this is just one possible application of a heuristic based on machine learning. Such an algorithm could be used also for other applications, for example, for other kind of robots. For robots with legs also need to have PID controllers that need to be tuned. Or, for example, during the coffee break we were talking about humanoid robots made by Boston Dynamics that we all have seen. They can do parkour, they can jump around and so on. So, and this kind of robots today have reached this level of autonomy because of this combination between traditional control algorithms like PID controllers with more advanced AI-based algorithms that are built on top. So we have different layers of intelligence, but the bottom layer, the low level, that is the one in contact with sensors and motors, it is still based on traditional control algorithms like PID controllers. And with this, I think I would like to conclude my presentation, and I'll be happy to answer your questions.
Thank you very much for your presentation. Please, any questions for the presenter?
I have a question.
Please.
Please.
When you compare the PSO and WSO, usually a meta-heuristic, if you run multiple times, the result may be different. Is your result based on statistical average of multiple runs, or is just a one run, single run?
We have used different cost functions. Yes, I will show you. So one of the main factor in the cost function that we have considered is called integrated time error absolute. And it's basically a measure of the performance of the system in terms of the tracking error and the control effort. It's a combination. So how precise is our end effector to reach the target position, but also in terms of control effort. So for example, you can say energy efficiency, right? So it's a combination of this. It's just one possible cost function that you can consider. So I'm not saying that in general WSO performs better than PSO or GWO. In this specific case, it performs better. Yeah. And again, I don't think there is an algorithm that beats everyone else, right? It just, in this case, within your set of hypotheses, it works better. Yeah.
Thank you.
And,
I have a question. So, because in heuristics or all the other algorithms that are working on some kind of a population,
Yep.
there is equilibrium state, which means that there is optimal number of the agents cooperating in the system. So, have you done any measures or have you done any research? What would be the optimal equilibrium state of the agents in your system?
Yeah, this is an interesting question, and we have done some preliminary assessment. So, for example, here we have a robotic arm with 3 joints, right?
Mm-hmm.
A good question is how can this scale if we add one more degrees of freedom to the robot, another link, right? And does it scale linearly? Probably not. We need many more agents, especially if we increase the number of degrees of freedom. So for example, we have another robot, it's a snake robot, which has 10 links. It's many more degrees of freedom, right? And we have done some preliminary tests there, and we need many more agents. Yeah, so it's a good question. I don't have an answer, but for sure it's interesting to look how does this scale. Yeah.
Okay. Thank you.
thank you very much. Any more questions? No, thank you very much for your very insight.